Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hello students, good morning. So in our last lecture we saw the methods of purification of organic compounds. What did we see? That usually when you synthesize an organic compound, it comes with the impurities. Lots of even reacted reactants are there. Some other auxiliary reactants are there that we add during the synthesis of the reaction. Or even if you extract the organic compound from the natural resources, even in that case, we see not only the desired compound, but some other compounds also get extracted along with this desired compound. So what do we need to do is to separate out this desired compound from the reaction mixture that we obtained after the extraction or the whatever after the synthesis of the compound. To do that, we follow certain methods that are called methods of purification of the organic compound. Means we are purifying the organic compound. We are using some experimental technique, somehow taking out just the pure compound and leaving the impurities alone with the reaction mixture. So these are some very important methods that we talked about, which we use for the purification of organic compounds. The first is sublimation, and then the crystallization, then the distillation, the few methods of distillations we saw, then the differential extraction, and then the chromatography and two methods of chromatography that we saw in our last lecture. And what we see once the organic compound is purified, we understand, we determine it by checking the melting and boiling points of the organic compounds. And we also match this melting and boiling points with the already reported melting and boiling compounds of the pure compound in the literature. Usually for the pure compounds, the melting and boiling points are very sharp. So at a very sharp point, this entire compound, the entire crystal of the compound, either it will melt or even it will evaporate. So and the sublimation coming out to the each methods, just briefly, the sublimation it is used for the sublimate when the organic compound is sublimable, means it which can if it can be converted directly using just heat from solid state to the gaseous state, and the impurities are non-sublimable. Then we use this method for the purification of organic compounds. The crystallization method is used for the organic compounds which exist in the solid state. So what happens, we try to crystallize the organic compounds from the reaction mixture itself, and then during the crystallization, if we get the pure crystals of the pure organic compound, crystals of the pure organic compounds, then this organic compound is crystal we can filter it out, and whatever the filtered the impurities will go away. So we get the pure organic compounds in the form of the crystal, and this we get when the organic compounds exist in the solid state at the room temperature. And then there are some other things that we see. Then we looked at the distillation. This is a simple distillation initially. The simple distillation is used mainly to purify when the means or to separate out volatile liquid from non-volatile impurities. Means if our compound is a volatile liquid and the impurities are non-volatile impurities, then in that case we use the method of simple distillation. The simple distillation method is also used when the two liquids are there. The organic compound is also a liquid and the impurity is also a liquid, but there is a large difference between their boiling points. Then also we can use a method of simple distillation. And there we use a round bottom flask. We take the reaction mixture, we heat it, and we see the initially the compound or the organic compound with boiling point is less, it will be evaporated and will let this vapors go through a condenser, and we see where while passing through this condenser we use the cold water through inlet and the hot water will go out the thing through this, and this vapors of the organic compound will be collected over a receiver. Once the compound with the lower boiling point is collected, then we heat the reaction mixture further to evaporate the compound or the organic compound or the liquid which is having a bit higher melting point, boiling point, and then we also collect that over in a separate receiver, and that is how we separate out these organic compounds, and whatever left over is just the impurities that are undesired products. However, if the difference in the boiling point of two liquids or mixed liquids are not very high, it's just a small difference, in that case, what will happen that even the at a given temperature, vapors of both the liquids will form, and a simple distillation will give you also the mixture of these two liquids. Then, in that case, we use methods of distillation that we call fractional distillation. And this fractional distillation, we use a fractionating column. And what happens, we take the reaction mixture, we heat it, and we heat, and this thermometer is there to just control the temperature, and how much heat or the temperature should the heat is should be provided here just to control the flame. And the compound or the organic liquid which melting point, sorry, boiling point is higher, it will function. The vapor pressure of that liquid will be less, and the one with the lower boiling point will have a higher vapor pressure. But once these vapors go up, usually the liquid which boiling point is more will start condensing here, and the condensation of the vapors of also the liquids which boiling point is less also happens. But as we move up, what happens, the vapors gets richer into the liquid which boiling point is lesser, and after till it is vapor reaches here, it will almost be pure in the component which boiling point is less, and that component will now after the condensation will be received in a receiver. What happens, depending on the difference in the boiling points of two different liquids, we choose the length of this fractionating column. And this fractionating column, they are available into different lengths, and they are also of different types, and then we can see some fractionating column right here. So this is a simple packed column, and this is a bubble plate column. There are two different types of fractionating column. And then the method that we saw was in distillation under reduced pressure. So this is also a distillation method, and this method is used when a liquid which is to be distilled, it decomposes before it reaches its boiling point. Or what happens, or if a liquid is there, its boiling point is very high. So in that cases, those cases, what we do, we use this method, distillation under reduced pressure, and what we do, we use a vacuum pump to reduce the vapor pressure here above just the surface of the liquid using the vacuum pump. And once the pressure just above the surface of the liquid is reduced, what we see, the boiling point of this liquid will also be reduced, or this compound will also be reduced, which is to be distilled, which is to be purified or separated. And under the, if the vapor pressure or the pressure above the liquid surface is reduced, the boiling point will reduce. And then if the compound was just boiling before just decomposing before the boiling point, now this boiling will happen at a lower temperature because the decomposition happens at a particular temperature. Now the boiling is happening at the lower temperature, so the decomposition will not happen. And now you can just evaporate the compound, condense it, and receive it into a receiver. Or even if the compound is its boiling point is very high, so as we know, even if it is very high, if the pressure is reduced, again the liquid will boil at a lower pressure, and so its boiling point will be reduced, and so it can be evaporated and then condensed and collected into a receiver. And then we saw the steam distillation method. This steam distillation method is also a specific method, and this technique is applied to separate substances that are steam volatile but immiscible with water. So substances, if the organic substances are, they can be evaporated or if they are volatile at around 100 degrees centigrade in the presence of steam. And so what happens, they will also form vapors once the steam goes into this at around 100 degrees centigrade. This compound will be evaporated, it will form vapors, and vapors of water in the form of steam will also be there. Both the vapor mixture will be collected, and the vapor mixture of that contains organic vapor of organic compound as well as vapors of water, means the steam. They will be collected over here, and since this compound is not miscible with water, so what happens? The water, if the distilled liquid is here and water is lighter than this distilled liquid, or if its density is lower than the distilled liquid, water will be forming a separate layer above the liquid, and this is the distilled liquid. Or if it is even it happens, the vice versa may also happen. If the organic compound density is lesser than water, so it will now float over the surface of the water, and the water will be on the water will be below the organic compound, and so there will be two separate liquids because the layers of the liquid, because they are not miscible. So in steam distillation, the liquid boils when sum of vapor pressures due to organic liquid, and that's the vapor pressure of the organic liquid P1, and the due to water vapor, and that because if the pressure is P2, becomes equal to the atmospheric pressure, and the atmospheric pressure, when this pressure becomes equal to the atmospheric pressure, then this kind of moment the boiling happens. This is what we already know. And this technique separates aniline from aniline water mixture that we know. And once this we obtain this the two different layers of the water as well as the organic compound using a separating funnel, we can just separate them out. So this is the separating funnel that we know. Then we looked into the differential extraction method, and this differential extraction method we use separating funnel. And this method is used when we obtain the organic compound into the water, into the aqueous phase, and but this organic compound that we obtained into the aqueous phase while doing distillation on many other reaction mixture or heating the reaction mixture into the water or in the aqueous solution. And once this organic compound is formed, and suppose this organic compound miscibility of this organic compound is more in another organic solvent, and if its miscibility is more in the organic solvent which is not miscible with water, then we can easily, what we can do, we take the organic compound which is there into the aqueous mixture, in the form of the aqueous mixture or the aqueous solution, we take into the separating funnel, and then we add a suitable solvent which could be a pure uh, organic solvent or a mixture of organic solvents, and then we just use them, shake them well, and the compound that is there into the aqueous phase, now it will move into the organic phase because its miscibility is more into the organic phase. And now we can separate out, as you can see, the before the extraction and after putting them and shaking well, what we see, this organic compound that was there here, that you can see just with the intensity of the blue color now has gone into the organic layer, and organic layer and this aqueous layer we can just separate them out. Again, this aqueous phase, we use this aqueous phase again, we take them out using the separating funnel. Now this aqueous phase we again put into another separating funnel. We has further some more amount of the organic solvent, then we again shake it well, again separate it out, and this we do iteratively for a certain steps to a fixed number of steps, and then what we see, the organic compound is almost separated out, is almost taken out from the aqueous phase into the organic phase. And now this organic phase means the organic solvent is there, you can distill this organic solvent and the compound that is there, you can take the compound into the pure form. Then we show the chromatographic techniques. The chromatographic techniques is the technique that we use to separate mixtures into their components and then purify compounds and test of the purity of the compounds. We also measure using chromatography. Mainly two different types of chromatography methods are there that we saw, that absorption chromatography and partition chromatography. Absorption chromatography, we see column chromatography as well as thin layer chromatography, as you can see here, and the partition chromatography, the most famous is the paper chromatography. And in the all the chromatography techniques, what we do, we use a stationary phase and an mobile phase. And this mobile phase is a suitable solvent which can also be called as dilute. So the stationary phase, the mixture of substances is applied onto the stationary phase, which may be a solid or a liquid, and a pure or a mixture of solvents or the gas is allowed to move slowly over this stationary phase, and that compound or the solvent or the mixture of the solvents or gas that allows to move over the stationary phase is called mobile phase, and if it is a solvent, we also call it elute. So the absorption chromatography, it is, as we saw, it is of two types: column chromatography or thin layer chromatography. Usually, the stationary phase that we use in this case is silica gel or alumina, and silica with you look at the column chromatography, use silica gel or alumina that is here that forms a stationary phase. And over the stationary phase, we put the mixture of the compounds. We also add here the glass pools so that this stationary phase will not move out while we open this cork. And so let's just okay. So yes. So what happens? And then we add a solvent or a mixture of solvent over the mixture of the compound. Now the solvent will percolate down. It will also dissolve these organic compounds. These organic compounds, our deep mixture of compounds, if suppose A, B, C, three compounds are there. They will also move along with this solute or the mobile phase, the solvent or the mixture of the solvent that we use here. And then we take out the solvent, uh, opening this stopcock. And so what happens as the elute comes out with the elute, this organic compounds or the mixture of organic compounds, they are different compounds, and so their affinity with the stationary phase will be different. They will be absorbed on the stationary phase, and because the absorption happens because of the interaction, differential interactions between different organic compounds and the stationary phase, so they will be absorbed differentially, and so their movement will also be differentiated. So some of them, the one which is least absorbed onto the stationary phase will move faster, and the one which is having the highest extent of that absorption or the highest the strongest interaction with the stationary phase will move least. And so in with that we see after a certain time we will see different bands of different organic compounds into the column. And once we obtain this, what you can do is either you can keep this solvent coming out, and then this will also move, and slowly in the different solvents you can collect these different compounds into different beakers or different beakers. Or what else you can do is you can just let this column dry, and if you can separately take these things stationary phase out and dissolve it into a suitable organic solvent, distill it, then also you can separate them out. The easiest way is to keep adding this solvent, and once this will, after moving slowly, it will come out to here. And once it comes out here, you take another, start taking another, take another beaker and collect this much of whatever this colored compound, this band comes completely comes out, take collect it into a different uh, beaker or different flask, and once then you distill it and get the pure compound. Then you do the same thing for if this compound is also desired, and repeat the same thing if this compound is also desired. And then we saw the thin layer chromatography. Thin layer, the principle is again the same because they both are absorption chromatography. Here also the stationary phase absorbs the components of the mixture. And here what we do, we use a glass plate. On this glass plate we take around 0.2 millimeter thick a layer of silica gel or alumina that we are considering here as a stationary phase. And once we take this around this very thin layer of this silica gel or alumina, then at a certain point we make a spot, and on that spot we put the mixture of the compounds, and then we put this entire this coated this glass plate coated with silica gel or alumina is called thin layer chromatography plate or chroma plate, because a thin layer of silica gel or alumina which is a stationary phase is applied over it, and so this is called thin layer chromatography plate for the chroma plate. And then we put this chromatography plate into a jar containing a suitable solvent, and at the baseline we put the spots of this compound or the mixture of the organic compounds. And once we put the contact is made between silica gel and this organic solvent, because of the capillary action the solvent will move up. This solvent could be a pure solvent or a mixture of organic solvents. Suitable solvent we use so that the mobility of this will be more. The mobility of the solvent should not be high. What is our purpose is to separate out these compounds, and the separation should also have a sufficient enough speed so that it will happen. It won't take a very large time, and also the separation must happen if the solvent will move much faster. All the things if the mobility, these ions, suppose these are different ions or different compounds, their mobility in a given solvent is same, then they all will move the equal distance and the distance, and then they will not be separated out. So what we do, use a pure suitable solvent, and so once the solvent start rising up, and when it starts rising up, what happens, this reaction mixture will also, different components will move rising up with a different speed because of their differential adsorption with the stationary phase, and so they will move to different distances over this thin layer chromatography plate. And once that is done, what we can do is we can take out this thin layer chromatography plate, and we can also measure to what distance from the baseline different spots has moved. And once you can get that, and what the distance moved by a substance from the baseline, suppose the substance here has moved to this distance, so from this distance to this distance is what the distance moved by substance from the baseline, which is x, and divided by the distance moved by the solvent from the baseline y. And if the solvent moves to this distance, usually solvent always moves to a larger distance than the organic compounds, because organic compounds, usually these molecules are heavier than the molecular weight of the solvent that we take. Just a minute. Yes, and so this ratio is called the retardation factor, and depending on the differential retardation factors, different components will be separated out. And once these components, what we see of some of the components, they have their own intense color, so we can understand this component has moved out to this distance. But there might be components we do not show any color on this chromatography plate or layer plate, thin layer chromatography plate. In such a case, would we use different techniques to see those are the different components. The spots of the colored compounds are visible on the TLC plate due to their original color. However, the spots of colorless compounds, so those compounds which are colorless, their compounds are invisible to the eye. But if they can flourish in the ultraviolet rays or the ultraviolet rays, light can be detected by putting the plate under the ultraviolet light. So we put this entire TLC plate into a ultraviolet chamber, and if this compound which is colorless, this can flourish, we can see the different its fluorescence, and we can observe how where this compound is. Or if the another detection technique of the colorless compounds is to put this entire TLC plate into a covered jar containing few crystals of iodine. And if the iodine reacts with this compound, and if iodine gets absorbed, so we will see the brown color that appears around the compound that is there. Or sometimes an appropriate reagent may also be sprayed on the TLC plate. For example, for the case of amino acids are also colorless compounds, and to what distance they have moved. To understand that, we use spray the neon hydrogen solution, and with the color, now the color appears, and we can recognize where the amino acid, to what distance amino acid has moved, and where the amino acids are currently the spot is on the TLC plate. Then the partition chromatography. The partition chromatography is that the thing is based on the continuous differential partitioning of compounds of a mixture between the stationary and mobile phases. And the example of partition chromatography is paper chromatography. And how the paper chromatography works, it is much similar to the thin layer chromatography. So in the case of layer chromatography, this TLC plate we put into a jar, and we also put a solvent, and it moves to a particular distance. And what we see in the case of paper chromatography, we use a paper and we make a baseline with a pencil. We apply the reaction mixture, and after applying this reaction mixture, what we see, we put it to a suitable solvent in a given jar. Now the solvent will start rising up, and with the rising up of the solvent, we also see the different components of the mixture will move up. And with that, different components will move to a different distance or to a differential distance, and so we will get this compound. Means these compounds will be separated out, and if the compound is colored, we can see the color, we can easily understand that, and if the compound is colorless, we use the technique to visualize that compound that we have already seen. Yes, the thin layer chromatography. And at the jar that everything is there. Now let us look into the qualitative analysis of organic compounds. And this qualitative analysis means suppose an unknown organic compound is given to you, and if someone asks you that what are the elements that are present in this organic compound, so how will you understand, how will you get what are the elements that are present in this organic compound is called qualitative analysis of organic compounds. Means to detecting, to finding out, to determining what are the different elements that are present in the organic compound is called qualitative analysis of organic compounds. The essential, the elements essentially present in the organic compounds are carbon and hydrogen. And that we know if an organic compound is there, it will at least contain carbon and hydrogen. However, there may be other compounds, maybe other elements, the heteroatoms. And these heteroatoms may contain oxygen, nitrogen, sulfur, halogens, or phosphorus that we already know. Let us now look into the detection of carbon and hydrogen. How will we detect whether the carbon and hydrogen are there in the given compound? Means even to understand whether this compound is an organic compound or not. If the compound is the organic compound, it must be having carbon and hydrogen. To detect the organic compound and to understand whether the carbon and hydrogen are there in this compound or not, what do? We just heat the compound with the copper 2 oxide, which is the cupric oxide. So carbon present in the compound is oxidized to carbon dioxide, and the hydrogen present in the compound is oxidized to water. So what we see is the carbon is there, and when this carbon reacts with copper 2 oxide, and when it is heated with the copper 2 oxide, what is the copper gets reduced. So plus from plus 2 oxidation state, it goes into 0 oxidation state, pure copper metal, and the carbon gets oxidized to carbon dioxide. So from 0 oxidation state, although this may not be the 0 oxidation, we can state, we can say, because this carbon is uh, in the organic compound, and what is the nature of the organic compound, what is the molecular formula of the organic compound, depending on that the oxidation state of carbon may vary, so that we do not know usually. But what we see, the carbon oxidation state of carbon is plus 4 in carbon dioxide, which is highest oxidation state carbon can possess or carbon can show. But in the organic compounds, when some hydrogen atoms are added to the carbon, then we see the oxidation state of carbon is less than plus 4. So what we see, any organic compound, usually if the hydrogen is added to the carbon, then the carbon's oxidation state will definitely be less than 4. And then if it is less than 4 and it goes to plus 4, this process is the oxidation process. And then two hydrogen, the hydrogen is there when it reacts with copper 2 oxide on heating, it again the copper gets reduced to copper metal, co-elemental copper, and then water gets hydrogen gets oxidized to water. Now this carbon dioxide, that is okay, carbon dioxide is produced and the water vapor is also produced. And how will we understand whether this is carbon dioxide gas or some other gas? Or even if this is water vapor or something else, it's a steam or something else. To understand the gas that is coming out is copper only, what we can do is we can collect that gas and then we add slaked lime to it. Slaked lime is calcium hydroxide. Once you add calcium hydroxide, it forms calcium carbonate. The white turbidity appears over there, and what calcium carbonate in the calcium hydroxide. And once the white turbidity appears, this calcium carbonate is sparingly soluble in water. And the solution of calcium hydroxide that we use actually, and white turbidity appears, and this is there. And so what we can understand that, oh, just the gas is carbon dioxide, and the carbon dioxide has come out from the oxidation of carbon that was there in the organic compound. Then the water can also be detected that we see obtains because of the oxidation of the hydrogen that was present into the organic compound. And in the organic compound, usually, yeah. So what we see, the organic, and so this anyway, yeah. So this water that is there, we use copper anhydrous copper sulfate. And anhydrous copper sulfate is white in color. Once it absorbs this water vapor, and the water vapor is the water of crystallization. It goes into the crystals of copper, and it what the copper sulfate get crystallized. If you remove the water from the copper sulfate, it will become anhydrous. The crystal will break, and so for the crystallization, water crystallization is important in the case of copper sulfate. And with that, the change the color, the copper sulfate is also becomes blue from white and blue, and it means that the gas that was there, it was contains steam, and that is means water. So we can understand carbon and hydrogen are there in the given organic compound. Now suppose if you understand, if you find out if the carbon and hydrogen both are there in the given compound or the given organic compound, we do not need, did not know a priorly whether this compound is organic or not, because we got it contains carbon and hydrogen, this compound is an organic compound. But this carbon compound is a hydrocarbon, means it contains only carbon and hydrogen, or it also contains some heteroatoms like sulfur or halogen, fluorine, bromine, chlorine, iodine, or the phosphorus or oxygen, nitrogen. To detect the other elements, what do? We do the specific test that is called Lassen test. To get the Lassen test is first, it is based on the forming sodium fusion extract. To form the sodium fusion extract, what we do, we add sodium metal into the organic compound mixture of that organic compound that is there, and we use distilled water. In the distilled water, this sodium will be dissolved, it will form NaOH anyway, and then if you heat it, if you boil this organic compound, taking into a distilled water means the water which do not contain any kind of ion. And then the sodium metal, if you heat it, what happens? The sodium reacts with the carbon, nitrogen, all the heteroatoms, including carbon in the organic compound, and forms different kinds of inorganic compounds which are soluble in water. And then the different kinds of organic compounds means that ions are there which are soluble in water, means if this is NaCl is formed, so Cl minus ion is there. So sodium when reacts with carbon and nitrogen that are there in an organic compound and heated, it forms NaCl. This is Na plus and Cl minus. The nitrogen, sulfur, and let me see, the nitrogen, sulfur, halogens, and phosphorus present in an organic compound are detected by Lassen's test. The elements present in the compound are converted from covalent form into the ionic form by fusing the compound with sodium metal. And this fusion happens with the sodium metal that we see in NaCl is formed. If this compound if this compound contains sulfur, so what happens? The sulfur sodium reacts with sulfur that is there in the organic compound, and it will form Na2S, sodium sulfide. If it contains a halide, halogen atom, so it will form halide on heating with the sodium that is already there. And so we can now we can take this compound as 2Na plus and S2 minus, Na plus X minus. So the carbon, nitrogen, sulfur, and halogen comes from organic compounds. They all come from the organic compounds. Cyanide, sulfide, and halides of sodium formed on sodium fusion are extracted from fused mass by boiling it with distilled water. And this is what I have already described. This extract is known as sodium fusion extract, and the extract that we obtain after this distill using distilled water, sodium, and organic compound, and heating it, we get an extract, and that extract is called sodium fusion extract. And sodium fusion extract contains not only if the compound contains sulfide, it will contain sodium sulfide, it contains halides, it will means organic compound contains halides, so it will contain sodium halide. If the organic compound contains nitrogen as well, it will contain sodium cyanide, and if it so differently, if it contains all sulfur, nitrogen, halogen, in that case it will contain all these compounds and all these ions, sulfides, halides, and all, and so on. So based on that, now let us look into the taste of nitrogen. The taste of nitrogen that we already see, we have made sodium fusion extract and sodium fusion extract. If the compound containing nitrogen, we will see there is a formation of NaCl. The Cl minus ions are already there. So the sodium fusion extract is boiled with iron sulfate, iron 2 sulfate, and then acidified with concentrated sulfuric acid. So the iron 2 sulfate is we add, and then we also acidify sodium fusion extract with H2SO4. What happens when we do this? The iron 2 sulfate is there. Iron 2 when it reacts with the cyanide ions, it forms a complex which we can call a hexacyanoferrate complex. And this iron here is in +2 oxidation state, as you can see, it's a ferrous form, and this is 4 minus. So x plus 6 into minus 1 is equal to minus 4. So x is equal to plus 4. So the oxidation state of iron in the hexacyanoferrate is +2. Now the what we also see, if the when H2SO4 is added, H2SO4 also oxidizes the sum of the iron, the Fe2 plus into Fe3 plus, and this Fe3 plus now can react with, then we can, it can interact with this, and this Fe3 plus it forms this complex, and this complex is called the name is already there. I think ferric ferrocyanate. This is called ferric ferrocyanate. This is Prussian blue in color, and this is the Prussian blue color. So you will see the formation of Prussian blue color, which tells or which infers that the compound contains organic compound or original organic compound. It contained nitrogen. So the formation of the Prussian blue color confirms the presence of nitrogen. Sodium cyanide first reacts with iron. You see the sodium cyanide means Na plus and Cn minus. Na plus will be there anyway in the solution. The Cn minus sodium cyanide first reacts with iron 2 sulfate, and iron 2 sulfate, this is liver, so Fe2 plus, and forms sodium hexacyanoferrate. So this is nothing but Na4 ApCN6 4 minus sodium hexaferrocyanate. Now the sodium hexaferrocyanate and these three molecules of this ion, so 3 into Na4 ApCN6 will react with 4 Fe3 plus ion, and these Fe3 plus ions are produced because of the oxidation of Fe2 plus into Fe3 plus by the reaction of sulfuric acid with Fe2 plus. And then the XH2, it forms Fe4, FeCN6 thrice, XH2 as a water of crystallization, and this is Prussian blue in color, and which confirms that the organic compound contains nitrogen. Now let us look into the test of sulfur. Anyway, up to here the formation of sodium fusion extract we have already seen. So the sulfide is already formed, sodium sulfide is already there in the sodium fusion extract. We can use two different methods to test sulfur, presence of sulfur in the sodium fusion extract, or the presence of sulfide into the to the sodium fusion extract that we have just prepared. The sodium fusion extract is acidified with the acetic acid, so we add acetic acid to the sodium fusion extract to just acidify it, to add a slight acidic condition to it, and then we also add lead acetate to it. And the lead acetate, if it is added there, so lead is there into the acetate, and this lead, when it reacts with the sulfide, and this it forms a black precipitate of lead sulfide is formed, and this black precipitate of lead sulfide confirms that the sodium fusion extract contains sulfide ion. Then this sulfide ion has come from the organic compounds while making the sodium fusion extract. And so the reactions we can see, the sulfide ion that is there into the sodium fusion extract. We have just acidified the sodium fusion extract with the acetic acid. And why we use acetic acid again? Because the sodium acetate that we are using, because it is soluble in sodium acetate, is soluble in water, and to have this if the different ions will be there, there may be interference with that, and so to add that we add acetic acid, to just avoid that we add acetic acid, and when the lead reacts with the sulfide that is already there, it forms lead sulfide, which is black in color, and it is also solid, it doesn't get dissolved in water, and it forms a precipitate, and with the black color precipitate we understand that it's the lead sulfide. And the second method to understand or to detect the presence of sulfide into the sodium fusion extract is what we call the sodium nitroprusside test. The sodium nitroprusside, and on treating the sodium fusion extract with sodium nitroprusside, this is the sodium nitroprusside. This is Na2 FeCN5NO is called sodium nitroprusside. The appearance of a violet color further indicates the presence of sulfur. So the presence of sulfur means the presence of sulfide in the sodium fusion extract and the presence of sulfur then into the organic compound. So the sulfide, when it reacts with the sodium nitrochloride, and this sodium nitrochloride means Na2APCN5NO, and we get this the red, it's reddish brown in color. But when this reacts with the sulfide, it forms NOS. So everything is same. It forms NOS, and also since S minus 2 minus is added, so the 4 minus charge comes over here, and now we have Na4APCN5NOS, and the color of this compound is violet. So in the case of nitrogen and sulfur, both are present in the organic compound called sodium thiocyanate is formed. So what happens if the sulfur and nitrogen both are formed already there in the organic compound? In that case, what happens in the case of the sulfide is not, we don't get the formation of sulfide. Instead, the formation of thiocyanate happens. The SCN minus happens. The formation of SCN minus happens into the sodium fusion extract, and it gives this sodium thiocyanate is formed. The sodium, carbon plus nitrogen plus sulfur, and nitrogen and sulfur are already there, and if it is organic compound, carbon will also be there. So it forms Cn minus and NaSC minus. As Cn minus, it reacts with Fe3 plus. So what we do is sodium thiocyanate, it gives gives a blood red color and no Prussian blue, since there is no free cyanide ion. So what we see in this case, there is no free cyanide ion, but instead of that, what we see a formation of thiocyanate ions. And this thiocyanate ion will react with this iron, the iron that is there in the sodium nitrochloride, and it will form FeSCN, and this is the blood red compound, which color is the blood red. And so the formation of blood red confirms that SCN was there, SCN minus was there into the organic compound, and if the SCN minus was there into the organic compound, it means that this organic compound was having nitrogen as well as sulfur as a heteroatom. And there will be 2 plus charge on this compound, because what we know, HCl minus, there is one negative charge, and when it forms a complex with Fe3 plus, a compound with Fe3 plus, but there is 3 plus charge here, 1 minus charge here, so net 2 plus 2 charge will be there in this compound. This is the iron thiocyanate. So what you can see. So if the sodium fusion is carried out with excess of sodium, and yeah, so if the sodium is not just in the stoichiometric amount, but if the excess of the sodium is taken out, the thiocyanate decomposes to ill cyanide and sulfide. And so in that case, even if the HCl minus is there, this thiocyanate, though it forms initially, but if the excess of sodium is added to the sodium fusion extract, what happens? This HCl minus ion will be dissociated into H2 minus ion, sulfide ions, as well as cyanide ions, Cl minus ions. And now we can get this. The ions give the usual taste, and then they will, these ions will give usual taste. The sodium nitrochloride test we can get for the sulfide, and then for the cyanide we get the Prussian blue color with the formation of this compound. Let us now look into the test for halogens. So the test of halogens, what we know, the sodium fusion extract is all that is already formed, because we have already heated the organic compound in the presence of sodium metal, and in the distilled water we have heated it. So the sodium fusion extract is already formed, and if the compound contains halide ions, so there will be formation of sodium halides that we already know here. With this halide may be chlorine, bromine, or iodine. And so what the sodium fusion extract is acidified with the nitric acid, and in this case get a taste of halogens means what will form enough sodium fusion extract, and we will add a small amount of the sodium fusion extract to take all these tests, and we will perform all these tests to confirm what kind of heteroatoms are there into the compound. If you don't see the taste of halogen, means halogens are not there. If you don't see the test for the cyanide, it means nitrogen is not there. Means if the Prussian blue, the test of nitrogen doesn't come, it doesn't give the Prussian blue. If it doesn't give the mm, this nitroprusside, sodium nitroprusside test, it means this also doesn't contain the sulfide ion. This compound doesn't contain the sulfide ion, and it doesn't get the halogen. It means this compound is a hydrocarbon. It doesn't contain any heteroatom, and it also doesn't give the test for the phosphorus as well. So what means if it gives a particular test, we perform all these tests from the sodium fusion extract. So we form the sodium fusion extract in the enough amount so that we can perform all these tests of different to determine the presence of different heteroatoms into the compound. So the sodium fusion extract, whatever the leftover is, we can take the sodium fusion extract into a small test tube, a small amount, and we can acidify with it with nitric acid and treat with the sodium nitrate. And what with again you see sodium nitrate. It contains anion nitrate. So here the acid that we use to for the acidification is nitric acid, which also contains nitrate. So a white precipitate which is soluble in ammonium hydroxide shows the presence of chlorine. So if with the treatment of sodium fusion extract after adding nitric acid and then again adding silver nitrate, if you see the formation of white precipitate, and if this white precipitate gets dissolved in ammonium hydroxide, it tells the presence of chlorine or the fluoride in the sodium fusion extract, means the compound contains chlorine atom or the chloride there. If the precipitate is yellow in color, if again the precipitate forms, means the precipitate, the yellow precipitate is formed, then there is a chance that the bromine is there into the compound. And this, if this precipitate which is yellowish in color, it's not yellowish, mm, it's of the cream color. If it is yellowish or the cream color of cream color, then what we do, we add the take out, separate out this precipitate, filtrate it, and we add we then add ammonium hydroxide. If this precipitate is just sparingly soluble in ammonium hydroxide, slightly soluble in ammonium hydroxide, its amount is still not completely soluble, but some of its mass gets dissolved in ammonium hydroxide. It tells the presence of, it confirms the presence of bromide ion in the sodium fusion extract, or means the bromide ion is already the bromide is there into the organic compound. And if the precipitate formed is yellow in color, if the precipitate formed is yellow in color and if it is completely insoluble in ammonium hydroxide, it means that this compound contains iodine atom, means iodide into the iodide, and the iodide and the sodium iodide is formed into the sodium fusion extract. So what we see, the X minus when it reacts with Ag plus of silver nitrate, so X minus plus Ag plus AgX forms. This X represents halogen, chlorine, bromine, or iodine. If it doesn't form any precipitate over there, it means this organic compound do not contain halogen atoms. Note here that the nitrogen or sulfur is also present in the organic compound. So suppose if the nitrogen and sulfur also present in the organic compound along with the halogens, in that case the sodium fusion extract is first boiled with the concentrated nitric acid. So in that case what will we do? We will first boil the sodium fusion extract in presence of nitric acid to decompose cyanide and sulfide of sodium formed during Lassen test. And so the decomposed cyanide and sulfide that will decompose into sulfate, and these ions could otherwise interfere with the silver nitrate test called halogens, because they are pseudo halogens, and the pseudo halogens is sodium this is formed, and even the Cn minus is formed, and the Cn minus can behave as a pseudo halogen or thiocyanate, means cyanide and thiocyanate both behave as a pseudo halogen, and they may also form the precipitate and confuse you confuse you thoroughly that this compound may contain a halogen, but what happens, it may not contain halogen, but what the precipitate that you obtain is because of the formation of thiocyanate or the cyanide. And let us, and this science would otherwise, and let us now look into the test of phosphorus, and the test This is the last heteroatom that may be present in an organic compound. So the compound that we see is heated with oxidizing agent, and once it is heated with the oxidizing agent, which could be the sodium peroxide, so the sodium fusion extract is not used for the test of phosphorus. What we use, we again use the compound itself. The pure compound is heated with an oxidizing agent like sodium peroxide, means Na2O2. The phosphorus present in it is oxidized to phosphate, and the phosphorus that is present in the compound, organic compound, is oxidized to phosphate, and the solution is boiled with the nitric acid and then treated with ammonium molybdate. And then the solution is treated with ammonium molybdate. The yellow coloration or precipitate indicates the presence of phosphorus, and then we see an yellow color which indicates the presence of phosphorus. So if we see the sodium, this is sodium phosphate, and then when you add nitric acid to it, and the solution is boiled with the nitric acid, what we see, the oxidized, after the oxidation, phosphorus present in the compound is converted to the phosphate, and the sodium peroxide, if you have used for the oxidation of the organic compound, so will see the formation of sodium phosphate. Now the sodium phosphate is boiled with the nitric acid, and when this sodium phosphate is boiled with the nitric acid, a very strong acid, we see the formation of phosphoric acid H3PO4, and this H3PO4 plus we see the formation of sodium nitrate. So the exchange of the ions happens, and so with sodium nitrate, and this H3PO4, the phosphoric acid, plus ammonium molybdate. When this phosphoric acid reacts with ammonium molybdate in the presence of nitric acid, we see the formation of ammonium phosphomolybdate. This ammonium phosphomolybdate means NH4 PO4 12 MOO3, and this compound is the yellow color, and it forms an yellow precipitate, and the presence of yellow precipitate confirms the formation of ammonium phosphomolybdate, and if the ammonium phosphomolybdate forms, it means compound must be containing phosphorus as well. So what we have seen till now, we have seen the qualitative test, means what are the elements that are present in the organic compounds. That is what we detect using this test that I have just described. However, what we may also need is to find out to what extent the different elements are there into the given mass of organic compounds. So suppose means how to find out the percentage composition of the organic compound. How will you find out the percentage composition of the organic compound? You can get the percentage composition of the organic compound if you exactly know in the given, if the mass of the molecular formula of the organic compound, uh, and if in the given molecular formula, what are the, if the molecular formula is the, then that is one thing. Another thing is if you get the percentage of the mass percentage of all the elements that are there into the organic compound, then you can easily find out the empirical formula of the organic compound, because this element is there in this much mass percentage. Then another element this much mass percentage. And with the mass percentage, we have seen the technique how you can get the empirical formula, and then also using vapor density how we can get the molecular formula. So with the molecular formula, you can, and if you know the different presence of different elements and also their masses or the mass percentage and molecular formula, you can easily calculate the vapor density, and you can easily calculate the molecular formula. And if you calculate the molecular formula with some other test, or even from the molecular formula, if the compound is very simple, you can easily tell the structure of the compound, and the compound may have the possibility, if compound is having the possibility of the presence of isomers, then in that case what we have to do, we may have to do some extra test to confirm the exact structure of the organic compound. So what we do, we this kind of analysis to find out the mass percentage of an organic compound, the mass percentage of each element into an organic compound is called quantitative analysis. So qualitative analysis just to know what are the different elements that are present into the organic compound. Once you know these are the elements that are there into the organic compound, then the next task is what is the mass percentage of each element that are there into the organic compound, and with that mass percentage you can find out again calculate empirical formula, and with the empirical formula you can obtain molecular formula, and if you from the molecular formula you may also understand, you may also write the structure of an organic compound if there is no possibility of the formation of isomers. If there is a possibility of formation of isomers, we may need to do some more experiments to confirm the exact structure of the organic compound. So the quantitative analysis of compounds is very important in organic chemistry. It helps chemists determine the mass percent of elements present in a compound. Earlier we have seen, and this is what I have already described earlier, we have seen that the mass percent of elements is required to determine the empirical and molecular formula, and use the mass from the mass percent we can obtain empirical as well as molecular formula. The percentage composition of elements present in an organic compound is determined by the following methods, and for different type of elements we follow different methods. Let us first look into the carbon and hydrogen. Both carbon and hydrogen are estimated in one experiment. As we see even in the qualitative analysis, we estimate the presence of carbon and hydrogen into a single experiment. Here also during the quantitative analysis, both carbon and hydrogen are estimated in one experiment. A known mass of an organic compound, and to do that, what do? We add a known mass of an organic compound. This we weigh the organic compound, a definite mass of the organic compound we take, and that will note down what mass of the organic compound we have taken in the experiment, and it is burnt in the presence of excess oxygen and carbon dioxide, sorry, and copper 2 oxide. So when this organic compound is burnt in presence of excess of oxygen and copper 2 oxide, then we see the carbon and hydrogen of the compound are oxidized to carbon dioxide and water respectively. So the carbon will be oxidized to carbon dioxide and hydrogen will be oxidized to water. And so what this can be a general chemical equation for this. CXHY, we do not know what is X and Y, it's a general equation. When it reacts with H plus Y by 4 molecules of dioxygen, so X, this is X plus Y by 4 molecules of dioxygen, we see the formation of X molecules of, or X moles of CO2 and Y by 2 moles of H2. And if you see here, this equation is already balanced equation. So the number of carbon atoms are X here, here also X in the product. Number of hydrogen atoms Y in the reactant, and Y divided by 2 into 2, so Y in the product as well. Number of oxygen atoms here is X plus Y by 4. In this case, we also see is 2X plus Y. There is some error, so just see this. So anyway, this qualitatively there is some, I think, mistake is 2 to, yeah, yeah, it is already there. This is 2x, it's correct. This is 2 into x, because this is O2. 2 into x plus y by 4 into 2. So y by 4 into 2, it will become y by 2. So 2x plus y by 2 oxygen atoms are there into the reactant, and what we see here in the product as well, 2 into x plus y by 2 into 1 oxygen atoms. So this equation is balanced. There is no mistake. So this equation is balanced. So actually what we take this kind of devices and we add pure dry oxygen to it, and this is what we call the combustion tube. So we are actually, what we are doing is we are combusting, we are just burning this organic compound in the excess of oxygen and dry oxygen we do not use. So it should not contain water vapor. So dry oxygen we use, and when we heat this compound, and the oxygen is already there, so this oxygen, and when this compound that are formed, it goes to the copper 2 oxide. This copper 2 oxide that we see moves over the gas of copper 2 oxide, and so this compound, so the carbon gets oxidized into the carbon dioxide and hydrogen gets oxidized into water. Now the gases that are formed, the steam, that water vapor and the carbon dioxide, this gas, and this will also contain some unreacted oxygen as well, means the excess of oxygen. Now the mixture of these gases is passed to this U tube. This U tube initially contains, the first U tube contains calcium chloride, and this calcium chloride, which is anhydrous, so it is hygroscopic, it will absorb water. And once it absorbs water, suppose initially you have taken X gram of calcium chloride, and now the mass of the calcium, maybe m gram of calcium chloride, and the mass of the calcium chloride is m plus n gram. Now after the passing of this gases, it means n gram of water is already added, it is laden with this calcium chloride, and it means the water that is formed, the mass of the water that is formed is n gram. And now the reaction mixture, the gaseous mixture will contain carbon dioxide and oxygen, and the carbon dioxide now will move to this carbon dioxide, the KOH that we add into this tube to another U tube, this mixture passes. And once this carbon dioxide moves through this U tube, what happens is, and this U tube contains potassium hydroxide or sodium hydroxide, and this potassium hydroxide and sodium hydroxide, when it reacts with carbon dioxide, it forms potassium carbonate or sodium carbonate, and so potassium and sodium carbonate are formed, and water molecules are also formed during this reaction. And the excess of oxygen, now that all the carbon dioxide is absorbed here, and the excess of oxygen will go out from this combustion tube, and thus whatever the amount, the increase into the amount of this U tube can be considered as the mass of the CO2 that get absorbed, and the water molecule that is also formed, the water that is formed here, it will be there, still there into the solution. So thus the mass of water produced is determined by passing the mixture through a weighed U tube, which is already weighed U tube containing anhydrous calcium chloride, which I have just said. Carbon dioxide is absorbed in another U tube. So water that is absorbed here, mass of water produced, is determined by weighing this. So we can weigh this initially before passing the mixture, before burning this, the combusting this, and after the combustion, what we can see, we weigh this again, and we can find out what is the mass of the water that is formed, and from the mass of water, we can calculate what amount of hydrogen that is sent into the organic compound, because the water that is obtained here is the hydrogen of that water is actually we obtained from the organic compound. So whatever the mass that we obtained for the hydrogen, that is what the mass, we get the mass of the hydrogen that is there into the organic compound. Now the carbon dioxide is absorbed in another U tube containing, in this U tube containing concentrated sodium, a concentrated solution of potassium hydroxide or the sodium hydroxide. These tubes are connected in series. So these tubes are connected in series. You can see one by one. And these tubes are again, so what happens, this tube initially we add calcium carbonate, we just to make this air again become dry, because if you add this KOH solution before, so some of the water vapor that will already be absorbed here in the KOH solution, because KOH solution contains OH minus ions, and so these ions may also form hydrogen bond with water, and some of the water will be absorbed here. That is why the sequence is also important. We add initially anhydrous calcium carbonate, calcium chloride, then we add concentrated KOH solution in another tube. So these tubes are connected in a series in a given sequence. The increase in masses of calcium chloride and potassium hydroxide gives the amount of water and carbon dioxide from which the percentages of carbon and hydrogen are calculated, and what will be the method to calculate this, that we will see just now. So let the mass of organic compound be in. So it's just a mass that we weighed before starting this experiment, before burning this organic compound into the excess of oxygen. Suppose if you have taken in mass, in gram of the organic compound. So mass of the water and carbon dioxide produced B, and we also let's just understand, you can measure the formation, the amount of the H2O formed by weighing the this U tube before and after the combustion, and this U tube, weighing this U tube before and after the combustion, this will give the formation of the amount of the CO2 that is formed. And suppose if that amount of the amount of water is m1 gram and amount of carbon dioxide that is formed is m2 gram respectively. So the percentage of carbon we can obtain, and how we will obtain, we know in the carbon dioxide the molecular mass of carbon dioxide is 44, and if this is 44, and in the 44 what is the atomic mass of carbon, is CO2 is 12 gram. It means if you take 1 mole of carbon dioxide, so 1 mole of carbon dioxide means 44 gram of carbon dioxide, it will contain 12 gram, means 1 mole of carbon is 12 gram of carbon. So if M2 mole of carbon dioxide is taken, in that case, sorry, M2 gram of carbon dioxide, in 44 gram, 12 gram of carbon is there. And then M2 gram of carbon dioxide 12 divided by 44 into M2 gram of carbon will be there. And then to take the percentage of carbon, what will we do? We take the mass of the carbon and we divide it with the mass of the organic compound, and then we multiply it with 100 to get the percentage of carbon. This is a simple procedure, and the mass of the carbon in the organic compound is 12 into M2 divided by 44 is what we have already got. That this is what we have already got, and with that if we divide this mass by mass of the organic compound that we have already taken, and then we get the fractional mass of this carbon into the organic compound, and we multiply this with 100 to get the percentage. So we will get the percentage of the carbon that is there in the organic compound. Now we can also get similarly the percentage of hydrogen, and the percentage of hydrogen, what is the m1 gram of water is there. So what we see, 1 mole of water, mass of 1 mole of water is 18 gram, that is the molar mass, and the 18 gram of water contains 2 gram of hydrogen. These two atoms of hydrogen are there, so 2 gram of hydrogen. So 18 gram of water contains 2 gram of hydrogen. Therefore, m1 gram of water will contain 2 divided by 18 into m1 gram, and thus this is the mass of hydrogen, and this mass of hydrogen, that we, all the hydrogen that we get into the form of water was already there initially into the organic compound, and so the mass of the hydrogen that we obtain into the organic compound, that's 2 into n1 divided by 18. If you divide the mass of hydrogen with the mass of the organic compound, we get the fractional mass of the hydrogen into the organic compound, and then multiplying it with 100, we get the percentage of hydrogen into the organic compound percent, or the mass percentage of hydrogen into the organic compound. So I should have written this percentage here, and also the percentage sign should be added here. Yes. Let us now take a numerical problem based on what we have learned just now. On complete combustion of 0.246 gram of an organic compound, gave 0. We obtain 0.198 gram of carbon dioxide and 0.1014 gram of water. Determine the percentage composition of carbon and hydrogen in the compound. So an organic compound is there, and we have taken initially what is there into the question, that is written 2.246 gram of organic compound is taken, and a complete combustion of, there is some grammatical, to complete combustion of 0.246 gram of an organic compound gave this gram of carbon dioxide and this of water. I think this is okay now. So what we know, the percentage of carbon, using this formula you can finally easily calculate M2. Here M is the mass of the organic compound and M2 is the mass of the carbon dioxide. This is the mass of carbon dioxide that we already see here. Please remember the M2 is the mass of carbon dioxide, and in this formula M1 is the mass of water that is produced, and this M is the mass of the organic compound. So the carbon dioxide that is produced is 0.198 gram of carbon dioxide. So 12 divided into 0. In this equation, 12 into 0.198 gram into 100 into 100, you see here, divided by 44 into n. N is the mass of organic compound. This you get 21.95%. So even from this you can easily, just the way we have derived this equation, you can also calculate it easily. What will it will 44 gram of carbon dioxide contains 12 gram of carbon. So 0.198 gram of carbon dioxide will contain 12 divided by 44 into 0.198 gram carbon. And once you get this gram carbon dioxide, and this carbon has come ultimately from the organic compound itself, to divide the mass of the carbon divided mass of the organic compound into 100 will give us the percentage of carbon. So this we get 21.95%. Similar percentage of hydrogen can also be calculated using the same method that we have described or using this equation directly. In this equation, M1 is the mass of water that is produced and M is that is produced means that is absorbed in the calcium carbon in the tube containing calcium chloride, and M is the mass of the organic compound, and MO the mass of the water that is produced is what 0.1014 gram, and so value of M1 we write here. 2 is there, 100 is already there, divided by 18. This is the molar mass of water into the mass of organic compound M, and this is 0.246. And solving this we get 4.58%, and this is how we solve this compound, and this we get the percentage of mass percentage of carbon and hydrogen. And what we see, to add this mass percentage of carbon and hydrogen, we don't get it 100%. It simply means that this organic compound also contains some other heteroatoms. It is not only the carbon and hydrogen that are present in this organic compound, means there are some mass percentages also attributed to some other heteroatom that are present in this organic compound. The rest of the things I'll just explain in our next lecture, next video. Let me stop the recording here. Okay, bye.